Hello everyone, welcome to this online talk on physics of language models, part 3, knowledge, storage, extraction, and manipulation. So this is my attempt to actually combine two papers into a single talk. Hope you will like it. So I told many of my friends that I work on the theory of language models, but what does the word theory actually mean? In my mind, it can mean actually a full spectrum of things. On one extreme, there is mathematics or learning theory, that is to define some concepts class, define data, define model, then make assumptions, and prove learnability theorems. So we love this because it's rigorous, you prove theorems, but there are also a lot of cons with it. For instance, the assumptions you make are typically too idealistic, and the networks you can analyze are often very shallow, like a two-layer transformer. And for those of you who have worked in this area, you may recognize that only in very rare cases, the theorems you can prove do actually connect to practice. So I used to work in this area as well, and we also wrote very long, like a mathy paper. In the end of the day, people may not even read it, may not even notice it. So for instance, a lot of people use LoRa fine-tuning nowadays, but very few of them actually knew that we had a paper before that published in Fox to actually study low rankness in feature learning. But very few people actually has noticed that. Celebi. In the other extreme, there is a type of study that I would call it as a metaphor, like ethology, that is animal behavior science, in which you play with, for instance, ChatGPT or Llama 2, and then to design tasks to make conclusions, such as is AGI coming or not. You can do this, and everyone likes it, and in this way you can study very large language models. And don't get me wrong, actually, you can also make conclusions that are very educational. But there are also cons with this. For instance, the conclusions you can make are typically very less rigorous, too subjective, and this may sometimes even lead to false claims. So there are many reasons I'm saying this. And for instance, nowadays, people have been calling for new evaluation metrics and benchmarks. One of the reasons is really because we are not even sure, for instance, if the pre-trained model on the internet data has cheated or not. So there was this sarcasm paper that showed up online about 4 weeks ago that says pre-training on the test set is all you need. This is, of course, a sarcasm. It's a paper, it's supposed to be a joke that says, like, if you put all the test data into the training, you get 100% test accuracy. You even observe grokking effect. But this is, of course, not what we want, right? But how can you be sure that the pre-trained model on the internet data did not see the test set? So for instance, like there could be some translated version of the test set showing up on the internet somewhere, like translating like from English to French, or maybe like tokenizing the test data set and then say add each token by integer one, and then put it on the internet. And what if like tomorrow the pre-trained model like looked over all the internet data and somehow has seen that? If so, then it could be cheating in terms of that evaluation data, right? So that's one of the many issues with respect to ethology. And in my mind, I think there is another very important issue here. That is, if you only play with ChatGPT, then it tells us very little about how and why things work or what's going wrong. So for such reason, in the past half a year, I have been really sitting down to think, is there any sweet spot in between the two? So this is an area, like I would call it as a metaphor, physics. That is, to design numerous controlled experiments and probe into the network to statistically uncover the mechanisms behind how diverse AI tasks are being accomplished via pre-training or fine-tuning. So I'm emphasizing on 4 words here. Number 1, I want to do controlled experiments. I want to control the data. I want to control the pre-train and the fine-tuning data, like designing synthetic data. And I want the experiments to be highly repeatable. For instance, this allows me to try all different configurations for the entire pre-training process and for the entire fine-tuning process. But this necessarily means that I cannot study a model that's too big. I can maybe like only talk about models on the scale of GPT-2. But fortunately, we do not need to analyze the entire AGI like as a single task. We can decompose maybe the notion of intelligence into some building blocks, and then to study them one by one. And finally, I'm emphasizing on the word probing. That is, I wish to really probe into the network, especially like if we're analyzing GPT-2, then that's of a smaller scale. We can analyze it, we can probe into the layers, into the neurons, to actually uncover what is happening behind the scene. So this is an area I would call it physics. I would perhaps not call it neuroscience because, at least to me, like back to 10 years ago, neuroscience is more like you buy 5 monkeys and you design 20 tasks. You put maybe 30 like electric probes into their brains, and you try to derive conclusions from there by collecting data. But here, like by probing into those language models, I'm talking about growing really like tens of thousands of monkeys from scratch. And you can control the data. You can control precisely what they have seen throughout their lifespan. And then you can design also thousands of tasks or tens of thousands of tasks. You can put millions of probes into everywhere of this transformer model. So this is more like experimental physics in my mind. So one thing I just said is that I wish to carefully decompose the word intelligence into building blocks and then design controlled experiments to study them one by one. So there are many such possibilities, and we are actually working on a whole series of papers to uncover the mystery behind it. And today I'm talking about part 3, which is regarding factual knowledge, or more specifically, knowledge storage, extraction, and manipulation. So later this week, I'm going to release another video talking about context-free grammar, which is not English grammar. English grammar is very easy to learn, right? But the context-free grammar can be some like synthetically designed, hierarchically designed logic structure. And over there, in that paper, we actually study how GPT-2 can learn such hierarchically defined grammar language. So that's another talk. In today's talk, I'm focusing on factual knowledge. Okay, so that's the topic. So to begin with, I want to actually show you some counterexample for GPT-4. So the first example is as follows. Suppose I ask GPT-4, like, was Barack Obama born in an even day? So it sometimes first gives me a wrong answer, like no. Although it seems to know that Barack Obama was born on October the 4th, and 4 is an even number, and therefore, like, it actually finishes the sentence by saying that, well, Barack Obama was born on an even day, although, like, it started with the wrong answer, no. So we have seen, like, not only this example, but many other examples with respect to other celebrities and so on, and not only for birthday, but also for birth month and birth year. So that's one type of counterexamples. Another type is when you're comparing, for instance, the birth dates of 2 celebrities, like Mike Connell and Joe Biden, to ask GPT-4 who was born earlier. Or was Mike Connell born like earlier than Joe Biden? So we notice that GPT-4 can sometimes give you a wrong answer, followed by the exact correct birth dates of the 2 celebrities. And then if you push GPT-4 to answer that again, it may apologize and then correct itself. So we have also seen like a lot of such counterexamples. So what is really happening behind it? So this is the whole point of actually this talk. So in principle, to study the question of, for instance, was Joe Biden born in an even year, then you can check the correctness of any language model such as GPT-4 or Llama and so on, and check the correctness with respect to, for instance, all the celebrities on Wikipedia. But this correctness does not actually alone tell you like really what's happening behind the scene. I claim that there are many, many subtleties that could possibly happen. For instance, the model may not even extract the birth year of Joe Biden, not to say like doing this even or odd test. And from there, there could be some other possibilities. That is, maybe the model just did not see Joe Biden's biography in the pretrained data. Or maybe the model has seen it, but the model is not fine-tuned enough to extract any birthday knowledge. Or it could be that maybe the model can extract birthday knowledge for certain celebrities, but not Joe Biden. So we actually spent an entire first paper to study under what condition the model can store and successfully extract knowledge, such as the birthday information about a person. And now suppose you're already super confident that the model can, for instance, extract birthday information about every single celebrity on Wikipedia. Now you can begin to test if the model can answer the even or odd question regarding the birthdays of every celebrity on Wikipedia, right? You can collect the data. But still, I claim that over there are two other possible subtleties. For instance, if the model answers this question correctly, could it be that the model has seen this data in the training? For instance, when we were first presenting this paper internally at Meta, I was using the example of Donald Trump. But after a few months, I noticed that Donald Trump was no longer a counterexample to GPT-4. So I thought about what could be happening here. That is, ChatGPT is actually refreshing its training data every once a month, I think. And after my talk, I think not only I tried this counterexample, many of my friends, many of my colleagues actually tried it as well. So it could possibly be that ChatGPT actually has memorized the Donald Trump counterexample, and they actually knew how to fix it, but only for Donald Trump. And that's why now we have to use Barack Obama, for instance, as an example, counterexample to this question. So therefore, even if the model answers correctly, it could be that the model is cheating, right? And conversely, if the model answers incorrectly, it could be possible that the model actually did not get fine-tuned enough to understand actually what even or odd means. So in fact, we spent an entire second paper to precisely eliminate, to do the controlled experiments very carefully to precisely eliminate the two possibilities sitting here. And if these two are eliminated, then we can finally study the model's true ability on manipulating knowledge. So this is the plan of today's talk. That is, I will first talk about under what condition the model can extract knowledge. And then I will study under the condition that the model can successfully extract knowledge, then how to do the correct controlled experiments to study the model's ability to manipulate knowledge. For instance, doing this odd or even test on birthdays. So that's the plan. To begin with, I will need to first define what do I mean by knowledge using our synthetic experiment. So here, I would love to define knowledge to be some biographical profiles of randomly generated individuals. So I'm going to prepare to you two datasets, the bio-S and the bio-R dataset. So S stands for synthetic, and R stands for real or semi-real. So in the bio-S dataset, I'm going to create 100,000 individuals. Each individual has a random name, first, middle, and last name. And then each individual also has 6 attributes: the birthday attribute, the birth city attribute, the college or university attribute, the major attribute, and the employer name attribute, as well as a work location. So all the first 5 attributes, birth year until employer name, are uniformly and independently randomly drawn from an underlying set of possibilities, except the last attribute, the work location. So this is uniquely determined by the employer's headquarter location. So for instance, if the employer is Meta Platform, then the city will be Menlo Park in California. So in this way, we designed a synthetic data in which most of the knowledge attributes are totally independent of each other, but 2 of them are completely dependent. So this is how we designed the bio-S dataset. And here, we use exactly 1 sentence to describe 1 attribute. And each sentence is randomly drawn from a pool of 50 English sentence templates. And for now, I'm also going to fix the sentence ordering. That is, the first sentence always describes the person's birthday. The second sentence always describes the birth city, and so on. So this is our bio-S dataset. Our bio-R dataset is just a simple additional, just applies a simple additional step on top of bio-S. That is to just simply apply llama 1 to rewrite the biography to make it more like real-life biographical entry. So this is how we create the 2 datasets. And now let me define what do I mean by knowledge extraction. So we have this biography data that we call, say, for instance, bio-S that contains 100K individuals. And now let me consider, remember each person has 6 knowledge attributes. I'm going to define 6 questions for the 6 attributes, 1 for each. For instance, what is the birthday of Anya? and the correct answer should be October the 2nd. And which university did Anya attend? The correct answer is MIT, and so on. And I'm going to divide the entire set of people into two groups: the training set of people and the test set of people, so half and half. So now I put half of the QAs into training and test the model's capability of answering those QAs for the remaining half of the individuals. If the model can do this, I claim that this means that the model can successfully extract knowledge about all of the individuals. So this is how I define knowledge extraction. So as you will see later in this talk, we will also allow for instance, adding Wikipedia or Common Crawl data into the pre-training. And this is okay because we're considering a synthetic data. So all of the names are randomly drawn, and therefore those names will not show up on Wikipedia. So therefore the model has no way to actually cheat. So this is one of the advantages of using synthetic data. So we have a total of 10 results today. So the first result I want to show you is what we call mixed training. In mixed training, we just put together all the bio data and all the QA data of the half of the individuals all together as the training data, with a ratio that we call QAR to control the number of tokens we see, like for the QA data. And 1 minus QAR is the fraction of them that we see from the bio data. So we put them all together into the pre-training, and we do the next token prediction test. So here is the result. The short answer is that if you use, for instance, GPT-2 of 100 million size for the bio-S data, or 300 million size for the bio-R data, then the mixed training test accuracy on the remaining half of the people is actually pretty good, like more than 85% for the bio-S and more than 75% for bio-R. So this means that mixed training works to a very good extent. And here, this ratio, QAR, had better be around 80%. That's the best tuned parameter in our setting. So this may look good, except that we also notice something very bizarre happening behind the scene. Namely, if we separate the two kinds of accuracies, that is the bio accuracy, and that represents the accuracy of correctly generating the 6 attributes on the bio data, and the QA accuracy with respect to answering correctly the 6 questions for the individuals on the training or test data. So we can separate these two kinds of accuracies. We can also separate the two kinds of people. The people whose QAs are in the training set, we call them in-distribution people, or Pretrain. And the remaining half of the people whose QAs did not show up in the training, we call them out-of-distribution people, or p-test. So therefore, we have this 4 kinds of accuracies that we can keep track of during the entire training process. Let's see like how they actually increase, or which one increases first. So in principle, there are even 8 accuracies to be precise. That is, in each cell here, you can talk about the whole attribute accuracy, that is to correctly answer the entire attribute, or maybe the first token accuracy, like answering, for instance, the Malo, this word, correctly. And the 2 accuracies, one is, of course, bigger than the other one, but the relative magnitude are really very proportional to each other. So therefore, in this talk, I'm not going to distinguish their difference. So let's think about it as only having 4 kinds of accuracies. And let's see like how they progress as mixed training goes. It turns out that the model at the very beginning uses the in-distribution QA data to encode knowledge, which is this amount of data. And this helps the model to memorize the in-distribution bio data, and therefore, like the in-distribution bio data's accuracy also quickly rises. Only after a long period of time, the model learns to align the encoded knowledge with the bio data to learn to also encode out-of-distribution bio. So the out-of-distribution bio accuracy actually increases much, much later. And this is finally followed by the increase of the QA out-of-distribution accuracy, or the test accuracy, in other words. So this process, if you think about it, is very bizarre because it does not reflect the natural progression of human knowledge acquisition. So think about it. For humans, for instance, me, I learn a lot of knowledge from textbook or from Wikipedia and so on. And later, like in life, I try to apply such knowledge to individual tasks or maybe by taking exams and so on. But this mixed training actually is following a different pattern. That is, it starts to learn knowledge at the very beginning using the QAs or using the exam data instead of using the textbook data. So this is like to study to pass the exam kind of approach at college, in which maybe some students take some exams from past years and then to first learn from there before even opening the textbook. So this is definitely not a natural process of human knowledge acquisition. So another issue with this is that it also does not connect to how people do language model training in practice. For instance, we are using this super large ratio of 80% of QA data in the training. But for instance, for Llama 1, if you go into the paper, they were only using 2% of the data from Stack Exchange, which can be understood as some QA type of data. But we were using like 80% of that. And why do we use 80%? Because that is required, that is like the best student parameter. And if you lower down that ratio, then the performance of mixed training actually greatly degrades. So this is what we found out in mixed training. It performs well, but it does not really connect to practice, or it does not really connect to natural progression of human knowledge acquisition. That is the first result. In our second result, we try to study a process that is more commonly used in practice. That is, we first do pre-training using the biography data, and then we do a fine-tuning process, or sometimes known as instruct fine-tuning, to fine-tune the model to answer the QAs using half of the individuals. And then we test its performance on the remaining individuals. So this is a three-step process: pre-training, fine-tuning, and then testing. Okay, people do this a lot in practice, and let's see like how it performs here. The short answer is that it performs very bad. So not only for the bio-S data, also for the bio-R data, not only for like a smaller model size, or we even increased the model size to 700 million parameters, which is much more than enough to encode the knowledge for those like 100K individuals. But in all of the cases here, the performance is pretty bad. So let me read this with you. In each cell, there are two numbers. The first number is the QA train accuracy, which is the accuracy of the QA during the training. And the second number is what we care about, is the QA test accuracy, is the accuracy here. So we see that no matter how you do fine-tuning, you can use full fine-tuning, in which case the performance is pretty bad. The training accuracy can go to nearly 100, but the test accuracy is only like 7%. And you can also do lower fine-tuning with respect to all kinds of lower parameters, but all of them just give you very bad test accuracy, like no more than like 10.5% during testing. So this is what we found out. So there are a lot of numbers like on this screen, but in fact, behind the scene, we tried a lot of, I would say like tens of thousands of possible fine-tuning and pre-training parameters, and all of them just fail. So how to really fix this? There is actually a very simple way to fix this. That is to do data augmentation. So remember that our bio-S data was prepared in such a way that each person has only one single biographical entry, and the 6 sentences are also written in a fixed ordering. So let's now consider 3 kinds of data augmentation techniques. One is to add data multiplicity by creating not only one biographical entry, but m distinct biographical entries per person. So talking about the same knowledge attributes, but using different English, like came to the world on this date instead of like was born on this date, or like originated from Princeton instead of spent her early years in Princeton, and so on. To add multiplicity, the second way is to add random permutations. So instead of using the first sentence to always describe the person's birthday, but we randomly permute them. Say that the first sentence can now describe the person's birth city, and so on. And finally, we can also replace the pronouns in each sentence with the person's full name, so that we repeat the person's full name 6 times.
So let's now see that by adding those data augmentations, or what we call knowledge augmentation, then how does this process change? So it turns out that the performance of this fine-tuning process actually can increase a lot. So let me explain this to you. So this, let us use like single to represent the original bio-S dataset. And let us use this multi-5 plus permute to mean that we generate 5 entries per person with random permute. And we see that if we do this level of knowledge augmentation, then the fine-tuning accuracy suddenly like shoots up to almost 100%. And here are the individual accuracies for the 6 tasks. And we originally only had about 10%, but now it goes to like 96%. And if you do things in between, for instance, if you only add multiplicity, even 5 times, that's not enough. You only get about 40% accuracy. And if you only add permutation, that's also not as good. You only get, you can do the random permutations 5 times, but you only get 70% of fine-tuning accuracy. And finally, if you only do permutation once, that's even the worst. That's even worse than before. Okay, so I'm not reading this like line by line to you, but the first very takeaway from this result is that the more knowledge augmentations you add to the pre-training data, then the better the fine-tuning accuracy becomes. So if you think about it, this is pretty striking because knowledge augmentation is actually a process about the pre-training. That is, it's about the pre-trained data. But the QA accuracy is a result of the fine-tuning process. So what I'm saying here is that the way you augment the pre-trained data will actually affect the downstream task performance. And for instance, in particular, if the knowledge is not augmented, like in the single case, that is, each person only has 1 biographical entry and the sentences are not permuted, then no matter how you fine-tune the model, the knowledge is not extractable up to this more than like 10% accuracy. So this is pretty striking because in all the cases, no matter if you augment the data or not, the model is capable of memorizing the entire training data, of like of doing the next token prediction task to nearly 100% accuracy for each individual on all the biographical entries. But in some cases, the knowledge is extractable using the QAs, but in some other cases, it's not. So if you think about it, this must be because that the model has stored knowledge in a different manner with respect to the different ways you augment the pre-trained data. In the next two results, results 4 and 5, I'm going to show you 2 probing techniques, and we will use that to explain how differently are the knowledge stored with respect to different knowledge augmentations. The first probing technique I will show you is what we call p-probing, or positional-based probing. Here is how we do it. We feed a biographical entry as input to GPT-2. And GPT-2 is a decoder-only model. It has, for instance, 12 layers. Then we take 6 special token positions, which are the prepositions right in front of the 6 knowledge attributes, like the on, the in, the at, and so on. And then we let the model take this as input and process for 12 layers. We look at the last layer. We look at the hidden embeddings of the tokens at the last layer, and we only focus on the 6 special token positions. And from there, we want to do linear probing. That is to add a trainable linear layer to predict the 6 possible knowledge attributes of this person. So we have 6 special positions and 6 tasks. So this total to 36 classification tasks. So, of course, if you are, for instance, at this position, and if you want to predict what is the employer name of this individual, that's very simple because the original task is next token prediction task. So that means if you are here, you should already know what's the employer's name by doing linear probing, for instance. But what we care more here in this p-probing is that given that this knowledge is memorized by the model, then could it be extractable from here, 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 or here, much earlier than the immediate previous token position? So this is what we care about. And let me show you the result. Let us first focus only on the probing accuracy for the company name, okay, which is our employer name for this task. And let us compile the following two rows. The first one is without any knowledge augmentation, and this one is with the best possible knowledge augmentation. So we immediately see a difference here. That is, in the first case, this knowledge about the employer's name of this individual is only extractable when you reach this token. And here, this accuracy means the accuracy of going from here to predict the employer's name. But if you were like anywhere earlier in those 4 positions, the prediction accuracy is pretty close to 0, like only 1 or 2%. But in contrast, if you do augmentation to the data by like adding permutation and adding multiplicity to the biographical entries, then the accuracies are 100 like everywhere. Meaning that even if you were very early on, right after the person's name, before the appearance of any attribute, already here, you can 99.9% extract the person's employer's name by using a linear predictor from here. Okay? In other words, if you think about it, it means that if you augment the data, then the model will actually learn the right logic. That is, it is Anya who works for Meta, because the knowledge of this Meta platform is stored only on this person's name. But in the other case, the model might be actually learning a wrong logic. For instance, it's somebody born on October the 2nd, 1996 in Princeton and studied communications at MIT who works for Meta. Because only when reading all the knowledge, only when after reading all the knowledge attributes about Anya, then the model actually can extract the knowledge about Meta platforms. So therefore, this knowledge may not be stored actually on this person's name if you do not augment the pre-trained data. So this is what we found out from this process, this probing technique that we call p-probing. So in the paper, you will actually see a more careful experiments in which we did even this variant diagram by precisely studying like the accuracy of probing depending on whether or not any of the remaining 5 attributes has been seen or not. So we did a very careful experiment over there by actually coupling all the 6 attributes into 3 pairs and making sure that one attribute always appears before the other attribute in the same pair. And then we noticed that the accuracy of probing actually of the second attribute always depends on the whether or not the model has seen the first attribute in that pair. So we did a more careful experiment than this one to actually further elaborate this finding. Namely, that is whether or not the model can successfully extract the person's knowledge really crucially relies on how early the knowledge has been stored, and preferably directly on the person's name. And our next probing technique is actually to more closely look at this. That is, this time, instead of feeding a biographical entry as the input to the model, let's only feed the person's name as the input to the model by adding like a special starting token and a special ending token. And then let's look at the hidden embedding of the model on the last token. And we do a linear classifier once again to predict the 6 attributes of this person. Okay, this is what we call Q-probing or query-based probing. And here is what we found out. So on the left, you will see the QA fine-tuning accuracy. And on the right, you will see the Q-probing accuracy. And you can see that the probing accuracy, although like have different numbers comparing to the QA test accuracy, but the entire pattern of the 2 tables actually look exactly the same. So this means that actually whether or not the model, whether or not the attribute is directly stored on the person's name is really a crucial factor for effective knowledge extraction. Okay, so this is what we found out using the second type of probing. To sum up, So far, I have shown you that whether or not knowledge has been augmented in the pretrained data, this would imply that whether or not the knowledge is nearly entirely stored on the person's name after pre-training process, and this will imply whether or not the knowledge can be extractable after instruct fine-tuning. And the reverse of this is also true. That is, if knowledge is not augmented in the pre-training process, then the attribute will not be entirely stored on the person's name, and then the knowledge just cannot be extracted after fine-tuning. So this is like the conclusion so far. Okay, if you think about it, a very strong message here is that if you really want the knowledge to be extractable, you had better augment the pre-trained data. And if you don't, then no matter how you do the fine-tuning, the knowledge may become just impossible to extract. So that's so far the message of today's talk. Let us now move to two bonus questions. Number one, do we have to augment everybody? Number two, many of the issues I told you earlier actually really is really connected to the spatial dependency of the words, like which word shows up before another one. And this is strongly attached to the unidirectional behavior of GPT. Then how about bidirectional model, like BERT, right? What will happen over there? So those are two bonus questions I'm going to answer right after this. The first bonus question is what we summarize as celebrity can help minority. So here is the experiment set up. That is, we consider two groups of people. One group of, again, like 100K people that we call minority, in which like we do not augment their biographical entries. That is, we let each person only have a single biographical entry without any multiplicity. And we also add random permutation that makes things even worse. So that was the worst possible scenario a few slides ago. And for the other group of people, we call them celebrity, we let their data, their biographical entries to be, in some sense, fully augmented. That is, each person has 5 biographical entries, and all of them are randomly permuted. So we put both kinds of people in the pre-trained data. So this really do connect to practice because some people like Joe Biden and the presidents and so on, actually their biographical entries really showed up a lot on the internet and with different wordings and so on. But there are some other people who, what we call like minority in this talk, their biographical entries only showed up maybe only once or twice on the internet. So this is like the motivation for this experiment. And let us now pre-train the model with respect to those two groups of people, and then fine-tune the model. There are two ways to fine-tune it. You can fine-tune it on the minority or fine-tune it on the celebrity. And then we care about the QA knowledge extraction test accuracy on the minority group. Okay, let's do this experiment. For instance, on the bio-S dataset, if you do not have celebrity, then remember that the QA test accuracy was only 4.4%. But now if you add celebrity data to the pre-training process, now if you do fine-tuning and the final test accuracy just boosts from 4.4% to more than 85% accuracy. And not only for the bio-S data, and also for the bio-R data. So that means celebrity can really help minority. That is, the male presence of the celebrity data in the pre-training process actually helps the model to better store the knowledge in a way that the knowledge, even for the minority group, can later be extracted. So one comment here is that adding Wikipedia doesn't help. If you do not have celebrity, and if you replace the celebrity data with, for instance, the Wikipedia data, or even Wikipedia plus Common Crawl, which was what like GPT-2 Pretrain was using, then this also doesn't help. So you really need the minority and the celebrity data to be of similar formats, and you really want to ensure that the celebrity data to be fully augmented in order to help the minorities. So in the paper, we actually did even more careful experiments by controlling, for instance, studying what will happen if the celebrity and the minorities are slightly different in formats, like one of them have full names, but the other one does not. Then we noticed that the accuracy will drop, for instance, from more than 85% accuracy to like 63% and so on. So therefore, like if you really want to get a good accuracy, you had better augment some people. You don't need to augment every people, but you had better really augment them in a way that the celebrity and the minority groups are of the same distribution. Okay, in this way, you can help the model to better memorize the knowledge and store them in a proper way so that later, if you extract knowledge for the minority group, that also becomes easy. So in the paper, we actually also looked into precisely why this happens by, again, doing probing. And we noticed that, for instance, if you add celebrity to the pre-training process, then the model actually tends to store knowledge to a much earlier position comparing to as if you do not have celebrities being present. So that was the way that we explained what happened behind the scene for this first bonus question. So the other bonus result I'm going to show you is with respect to bidirectional models. Remember that GPT-2 or most versions of GPT is actually a decoder model that is during the attention process, it only reads tokens to its left. But in a bidirectional model, we typically study a masked language modeling task. That is to mask out a few words on the original sentence and then let the model actually to fill back what are the missing words. And in such a case, we can do the full attention matrix. That is, we can allow every token to attend to every other token. So we can also read to the right. So let's now look at if we do like masked language modeling on this decoder, on this encoder model, such as BERT or dBERTA and so on, then let us see that how does the process perform. That is, we can also do like a pre-training and then a fine-tuning and then test the model's performance on knowledge extraction. Let's see like how things would change. So it turns out that the result is actually pretty bad. So even with mixed training, recall that mixed training was better than pre-training, than fine-tuning, and so on, right? So even with mixed training, even with the strongest possible knowledge augmentation we have created, that is with multiplicity, with permutation, with full name, then the best possible knowledge extraction accuracy is only 41%. So that is pretty bad. And another important observation here is that the only knowledge augmentation we noticed to be useful is actually the full name augmentation. So if you think about it, this makes sense because in masked language modeling, each word has an equal chance of being masked. And the model actually tends to learn to associate knowledge words with the most related unmasked word, preferably those that are adjacent, right? So therefore, if you have full names like everywhere, then the model actually tends to store knowledge better onto the name of this person. If you also look at this table, you may notice also something weird, that is, for the 6 attributes, the accuracies are really not uniform. So some of the attributes can be extracted very successfully, for instance, the birth date of the person. And if you think about it, what's happening here is that a birthday is almost always like a 3-word pair, that is the birth month, the birthday, and the birth year. And the 3 words are quite independent. So you cannot infer this person's birth month from this person's birth year, for instance. So this makes the model unwilling to associate the 3 words actually among themselves. And therefore, the model will be more inclined to actually link them to the person's name. But for some other knowledge attributes, like the company name, in such a case, the company name can have multiple words, right? Like Meta Platform or Best Buy or Trader Joe's. In such a case that the 2 words are highly correlated in a way that the model will maximize their associations like among this attribute and inhibiting the storage of the knowledge actually to the person's name. So this is why that when you do knowledge extraction for an attribute like company name, then the accuracy will be very bad. For some other attribute, like the college major, you will also see like a high accuracy, but this is because most of the majors are actually single-worded, like mathematics, physics, or communications, and so on. So in such a case, that the model will also have to associate those knowledge attributes to the person's name, and so on. So you see that for this bidirectional model, only in very rare cases when the knowledge attributes are like single words and independent of each other, only in those rare cases the knowledge can be stored in a way that can be extractable. But in most other like more general cases, the knowledge just cannot be extracted. So we also did actually Q probing to the bidirectional model to further actually testify this. That is, we noticed that whether or not the model is, whether or not the knowledge is stored on the person's name actually will be proportional to the QA test accuracy of knowledge extraction. So therefore, like our probing technique actually applies more generally, in particular to bidirectional model as well. So this is our second bonus result. So far, I have shown you actually our most of the results for our first paper that talks about under what condition the model can store knowledge in a way that later the knowledge becomes extractable during the fine-tuning process. So for the remainder of the talk, let's imagine that suppose we already have a model that can 100% extract knowledge. Then how good can the model be at manipulating such knowledge? And we're going to study actually 3 basic manipulation tasks: knowledge partial dual retrieval, or knowledge classification and comparison, or knowledge inverse search. So we study like those 3 knowledge manipulation tasks. The first one of them is knowledge partial and dual retrieval. So remember, we have this bio data, right? Let me define knowledge partial retrieval as follows. That is, we ask for this person's birthday in the month, or maybe birth year of this person, instead of asking for the entire birth date, which has 3 words, right? So we ask for the birthday or the birth year of this person. We call this knowledge partial retrieval. And we also consider knowledge dual retrieval. That is to ask 2 knowledge attributes at once. Maybe say the birth city first, then the employer name, or maybe the employer name first, then the birth city, and so on. So we consider 6 knowledge dual retrieval tasks. And let's see like the model's performance on these 2 tasks. Again, we do fine-tuning and testing with half people for the training and half people for the testing, the same as before. So here is the result. Already something very interesting is happening actually on this page. So first, for knowledge retrieval, you can notice that for some of the models, with respect to some of the data augmentations, then the model is capable of nearly 100% extracting the knowledge, the full birthday information about this person. But the model may struggle on, for instance, extracting the birth year of this person. So this may appear absurd, right? Let me explain to you what's happening. So the birth dates are always like 3-worded, and we are using like the US format of birth date. That is, the birth month will show up first, then the birth city, then followed by the birth year. So in such a case, we notice that although the model is capable of extracting the entire knowledge, but if you ask the model to actually directly say the birth year, the accuracy is bad. So if you think about it, this means that this October the 2nd can be viewed as like a hint word. So once the model sees this hint word, it's capable of generating the birth year. But if you ask the model not to spell out the hint and directly say the answer, which is the birth year, then the model is not capable to be fine-tuned to do such a task. So we view this as actually the initial evidence for the necessity of using chain of thought or hint when doing some knowledge tasks. That's like knowledge partial retrieval. And for knowledge dual retrieval, also like something interesting is happening. So at the very first place, you can notice that if a model is capable of extracting all the knowledge, then dual retrieval is easy. So then extracting two knowledge at once, no matter which order you ask them, the accuracy is pretty high. But we also notice some exception. For instance, here, in such a case that you notice that if you ask the model to first answer the employer's name and then the work city of the person, then the model is capable of doing that to close to 100% accuracy. But if you reverse the order to ask for the person's work city first, then by the employer's name, then the accuracy is pretty bad. So what's happening here is because we designed this work city attribute to be completely determined by the employer's name of this person. Remember, if the employer name is Meta Platform, then the city will be Menlo Park. If the employer's name is Google, then the city will be Mountain View. If it's Microsoft, the city will be Redmond, and so on. So we made it completely dependent on the person's employer's name. And that means if the model is capable of, for instance, extracting the employer's name of an individual, then in principle, the model also knows about the work city of this person because it's uniquely determined by the headquarter position of that employer. But if the model first spells out the employer's name, then you ask the model, like, what is the birth city about this person? Then, what is the work city about the person? Then the model is capable of doing that. But if you ask the model to first spell out the work city of the person, or maybe if you ask the model to only spell out the work city of the person, then the model cannot do this. So once again, the model needs to use the employer's name as a hint in order to extract another knowledge, which is the work city of this person. So we view this actually as another initial evidence for the necessity of using chain of thought for some knowledge tasks. So this is what we found out for knowledge partial and dual retrieval. So that's the first of the three tasks we study. So on the next slide, I'm going to show you knowledge classification and comparison. So as it turns out, this is even a simpler knowledge manipulation task comparing to partial or dual retrieval. And over there, you will see that chain of thought is also needed. So what do I mean by knowledge classification? Very simple. For instance, was Anya born in an even month? The answer is yes or no. So I claim this is, I would say, perhaps the simplest possible knowledge manipulation task because I am talking about only a single knowledge attribute, not even dual like retrieval, just a single attribute. And I'm talking about a single word, a single token, that is the birth month, right? So therefore, like we don't have that partial retrieval kind of issue. So a single knowledge attribute, a single word, and the simplest possible machine learning task, classification, from 12 months into 2 classes, even or odd. Okay, this is like the knowledge classification task. And we can also do like a mod 6 or maybe mod 12, which is to convert it from words to numerals and so on. And we also study knowledge comparison. Like for instance, was Anya born in a month of a year that is later than Sabrina? The answer can be yes or no. And this is again comparing just a single knowledge attribute in a single word with respect to 2 people. Or maybe like subtracting the 2 months and so on. So we study those tasks, and once again, we do like a pre-train fine-tune process. And let me explain the process now very carefully. That is, this time we take a data set, a pre-trained data set that is already fully augmented. Okay, for instance, like each person has 5 biographical entries, and say all of them are also randomly permuted. So a few slides ago, I already showed you that if you do the knowledge extraction fine-tuning, then the test accuracy will be close to 100%. So this is because we are using the fully augmented pre-trained data. So that was like the first half of the talk. And now I propose to do a second layer of fine-tuning, that is to do a knowledge manipulation fine-tuning task with respect to one of the tasks sitting here. You can do this on half of the individuals and test it on the remaining half of the individuals and see how the performance goes. So this is the setting. And in fact, if you think about it, you don't necessarily need to do the first QA fine-tuning. You can directly, from the pre-train model, to jump to the knowledge manipulation fine-tuning. So you don't need to do the first step. So in fact, we're testing both. Okay, you can do the QA fine-tuning or without it. And let me show you the result. So first of all, although I wrote here like half of the individuals, but actually we did a more careful experiment by trying even fewer number of the individuals in the fine-tuning. So this way we can actually test what is the sample complexity needed for the task. And here are the observations. The first observation is that actually it does not matter if we skip this first step of the QA fine-tuning or not. So if you skip it, we call it the pre-trained model. Or if you first do the QA fine-tuning and then do the second round of fine-tuning, then we call it the QA fine-tuned model. And as you will see that the accuracy pattern are like almost the same in the two cases, and therefore like it doesn't matter like if you skip this or not. So you can feel free to think about it as this or that, and the results will be the same. And now comes a very surprising observation. That is, for this very simple task, perhaps the simplest possible manipulation task of classifying the months into even or odd categories, this actually surprisingly requires 50K samples to go to 95% accuracy. In contrast, classical machine learning theory tells us that you only need about, say, 100 samples to classify 12 months into two classes. And here, like the word embeddings of the 12 months, we indeed verified. They're pretty orthogonal of each other. So that is pretty bad. And if you do comparison, things are even worse. Then you only get 88% accuracy. The only simple task here is the renaming task. That is, if you rename from the English words like January through December to the numbers like 1 through 12, then the accuracy is good. So to conclude, I just showed you that during this second round of fine-tuning, although the training accuracy can actually go to 100% for half of the individuals or maybe even fewer of the individuals, but on the test set, this accuracy can be quite bad. And therefore, the performance does not out of distribution generalize to the test set, unless you have really a lot of fine-tuned samples in a way that's really more than like theoretically needed. So this is our observation so far, and then let us see like how to fix it. The way is easy, is to use chain of thought. So chain of thought is can be very easily defined as follows. That is, for instance, for this even or odd test, instead of letting the model directly spell out yes or no, you can let the model first spell out what is the actual birth month of this person, and then do this logic test of like, is it even or odd? Or for instance, if you're comparing two individuals, then you can ask the model to first spell out the birth months of the two people, and then do the yes or no question. Okay? So this is what we call a chain of thought, or maybe hint, with respect to the knowledge classification and the comparison tasks. And we can add both kinds of data, with or without chain of thought, to this fine-tuning task. And also we can test the model's performance with or without chain of thought. And let us see like what the result would look like now. It turns out, once again, the training accuracy, the fine-tuning accuracy can go to 100%. So what really we care about is this like test error. Here's what we find out. First of all, once again, it does not matter if you skip the QA fine-tuning process. So you can directly jump to the second round of fine-tuning, or you can do the first fine-tuning, then the second fine-tuning. The results are similar. That's the first thing. The second thing is that if you look at the model's test performance with or without chain of thought, then you can see two very different results. So if you look at the test performance with chain of thought, then we see that the accuracy greatly improves. And it's improved actually to a level so that the test accuracy is actually, in some sense, precisely equal to the accuracy of whether or not the hint has been correctly generated. So this accuracy, you can actually do the math. It's almost the same as the probability of the hint being correctly generated times 100% plus if the hint is not correctly generated, then say you randomly guess an answer. So this accuracy can be almost like line by line, calculated from the hint accuracy and so on. So therefore, like this conclusion is somewhat like believable. That is, once you add chain of thought, then the accuracy like greatly improves comparing to without chain of thought. But the next observation is what really like surprises me the most. Namely, during the inference time, if you do not do chain of thought, then the accuracy is still pretty bad. As bad as if like you never had chain of thought in the training. So let me say this again. That is, during the fine-tuning process, you can add chain of thought, right? But during the testing phase, you can check if the model actually has used the chain of thought data to actually improve its performance on the non-chain of thought data. And for instance, you can test the model's performance without chain of thought. But you notice that even when trained with chain of thought data, during the inference time, chain of thought is still required. And this, if you don't, then this accuracy would look almost the same as if you do not have chain of thought in the training. So let me make an analogy. In real life, as a human being, then we read a lot of data with chain of thought, right? Like math questions with intermediate steps and so on. But during the inference time, when you're confronted with a simple math question, typically you do not need to spell out the intermediate steps. Although maybe you do this by heart, but you do not need to say it out. But with the current architecture of language models, they have to say it out. They have to say this chain of thought. They have to spell it out. If not, if you force it not to do so, then no matter how good it's trained on the chain of thought data, then when you're testing it without chain of thought, it can be pretty bad. So this is striking to me because if you think about it, suppose you have like a 12-layered GPT or even a 100-layer GPT, right? Then the model could, at maybe the 10th layer, already be able to extract knowledge. For instance, the birth, the birth month of a person. So it has another like 90 layers. So like from the existential perspective, the model is capable of using the remaining like 90 layers to actually do a manipulation task, like for instance, the even odd test. But if you fine tune it, it cannot find such a solution. You have to really say it out in the next token, actually the person's birth month explicitly before like you can do this even or odd test. So this is like our finding for the knowledge classification and comparison task. And finally, we use this birth month as an example because it's the simplest possible task, right? And if you do some slightly harder task, like for instance, ask the model to classify like a major among 100 possible majors, or if you ask the model to compile two majors of two individuals, then the accuracy is as bad as random guess if you don't have chain of thought. So in such a much harder task, then you see that the model's performance is pretty bad, and you really need chain of thought, both during training and during testing. So this is what we found out for knowledge classification and comparison. So we also connect this to practice, especially to this context example I showed you earlier. So in the paper, we actually did a more careful experiments by selecting, say, around 5,000 celebrities on Wikipedia. We made sure that the model actually knows them. For instance, GPT-4 is capable of extracting the birth dates of all of those celebrities. But if you ask GPT-4, was this person born in an even month, then it's almost like just random guessing. And similarly, if you ask the model to compile two birthdays of two individuals that were born like close to each other, like say within 10 years, then the model's performance is also like random guess. So on this page, this is not our main result. It's in some sense ethology, that is to play with GPT-4. And we noticed that GPT-4 is also not capable of doing knowledge classification or comparison without chain of thought. So we view this as actually an evidence that is, even if you scale up the model size, the findings of our paper still apply. But once again, this is ethology, this is not physics. And our main contribution of the paper is actually to do this controlled experiments with the synthetic data to discover this phenomenon. And on this page, we're just connecting this to practice. So that concludes our results for the classification and comparison. So lastly, in this talk, I want to show you knowledge inverse search. And here is how I define this task. So we have this biography data, right? And this biography data has a special property that is the person's name almost always shows up at the beginning of the entire paragraph. And therefore, there is a very natural way to define knowledge inverse search. That is to ask this person's full name given the person's attributes. So we designed, in fact, 10 different such tasks. For instance, give me the first/full name of the person born on like October the 2nd, 1996. Or like we can even provide the model with all the 6 attributes of the person and let the model fill in what is the name of this person. So we designed 10 different tasks, and those are knowledge inverse search tasks. And we can again do the same thing as before, that is to first pre-train the model with even the fully augmented data like before, and then we can fine-tune the model on this knowledge inverse search task here with respect to, say, half of the individuals and test the model's performance on the remaining half. That's one way. We can also do mixed training. That is, we can put both of them together with a ratio controlling the frequency of tokens, like with respect to each of them, right? You can also do mixed training. And we noticed that regardless of how you do this process, you can do mixed training or fine-tuning, pre-training and fine-tuning. And for all of the 10 knowledge inverse tasks, the test performance is pretty bad as random guessing. So the first moment when I saw this, I thought maybe I had a bug in the code, right? It turns out we don't, and here's maybe one way to convince you, that is, let's now change the data by, for instance, instead of putting the person's name at the beginning of the first sentence, we put it, say, at the end of the first sentence or the end of the second sentence or the end of the entire paragraph. So we created like a few like other possibilities. And if you define data in that way, then the model's test accuracy just suddenly boost to something even close to 100% in some cases. So of course, this is cheating, right? If you move the person's name to the end of the paragraph, then it's no longer knowledge inverse search. But this is just a side comparison to maybe convince you that my code does not have a bug, right? So what we care about are really the rows sitting here. So those are knowledge inverse search. And as we see that language models are just incapable of doing knowledge inverse search. So the moment we saw this, like, we were very surprised, and we immediately tested this on GPT-4. So we had a lot of like experiments we did, and here's one of them. That is, we took Jane Austen's novels. So she had 6 novels, or on public domain, so we have the right to use them. And we can ask GPT-4, for instance, what is the sentence after a sentence, or what is the sentence before a sentence, and compare the accuracy. We noted that, for instance, GPT-4 is capable of generating the next sentence in Pride and Prejudice with a super high accuracy of like more than 65%. But if you ask for what is the previous sentence, then GPT-4 only has like a 0.8% accuracy, pretty bad. So this is an evidence that even if you scale up the model, then the inverse knowledge search task is still like a very hard task, for instance, for GPT-4. So the moment I showed this to some of my friends and colleagues, then a few of them were actually not surprised. They say that even for humans, inverse knowledge search is hard. But I want to defend a bit by saying that we had better have a fair comparison, right? Because for humans, then even for like Jane Austen's novel, I cannot even do forward search. So I have to like define maybe a more natural task for human beings. So here are the 2 tasks that came up in my mind. So as a Chinese native speaker, so I came up with like 2 Chinese examples, but I will explain to you what they mean. The first task is to study like Chinese idioms. So Chinese idioms are 4-character words and we can mask out one of the 4 words, like the first, the second, the third, and so on, and then ask, for instance, GPT-4, what is the missing word, right? For humans, if we mask out the first character in the idiom, then I think most of my friends is capable of like answering this question, like what is this X? But if you ask GPT-4, it's not capable of doing this task very correctly. So if you mask out the first character in a Chinese idiom, then GPT-4 only has a less than like 20% of accuracy of answering what is X. But if you ask for like what is the third character or what is the fourth character, the accuracy like is pretty close to 100%. So this is like one task in which I think human beings can do this inverse knowledge search, but with the current architecture design of language models, even GPT-4 cannot solve. So another task is this like Chinese poem task. So in Chinese poems, we have some very like famous and frequently used like sentence pairs. Like the first sentence and second sentence, the pair like forms like a commonly used Chinese poem sentence pair that we even speak like in our verbal language. And you can ask GPT, for instance, what is the sentence before the second sentence, or what's the sentence after the first sentence? And once again, like many humans can do this knowledge inverse search, or at least many Chinese speakers, like among my friend circle, but GPT-4 is not capable of doing that. And we tested that the GPT-4 only has like 7% accuracy of saying what is the first missing sentence, comparing to what is the second missing sentence, in which like GPT-4 has more than 66% accuracy. So we use this actually as like evidence to say that RAG is really necessary. That is, retrieval augmented generation is necessary with the current architecture design of language models. Namely, like you had better really add Google search into as a plugin in order to do knowledge inverse search, because language model just by design is not capable of doing that. And on top of that, I also want to claim that RAG may not actually be the end solution to all the knowledge inverse search tasks, because as a human, then there are certain like very commonly used knowledge that maybe humans can do inverse search, but GPT cannot. And for instance, when you're saying those like Chinese verbal sentences like to your friend and so on, you typically do not do Google search, every second or and so on, right? So therefore, for some knowledge, we probably do want the model to really memorize it well to a way that it can do inverse knowledge search. So then how can we do that? In the paper, we actually noticed one possible solution to this inverse knowledge search question. This is actually a solution found by GPT-4, so I will explain to you what this means. That is, let's take, for instance, the Bible and design a task of asking GPT-4, what is the verse before a verse, right? This is an inverse knowledge search question. So originally, I was actually thinking of using this as a counterexample to GPT-4, but then I noticed that GPT-4 is capable of answering this inverse search question with a very high accuracy, like more than 95% accuracy. And here is how it manages to do so. It actually uses chain of thought as a way to do this inverse knowledge search. Let me explain what this means. So the Bible is actually a very frequently found type of knowledge on the internet. And in fact, the Bible's verses are typically showing up on the internet in one of the two ways. That is, sometimes the chapter or the verse / verse number showed up at the beginning of that verse, or sometimes that showed up at the end of the verse. So the Bible is, in some sense, sufficiently augmented in the pretrain data with the chapter / verse numbers sometimes at the beginning and sometimes at the end. So this allows the model to actually do this knowledge extraction from the number to the verse and from the verse to the number, bidirectional. And this is good. And it allows actually the model to solve this knowledge inverse task using chain of thought, because it only needs to first extract what is the chapter / verse number from the given verse, right? And then it can do this simple math question to subtract it by 1, and then extract the verse from this new number. So we found out that GPT-4 is actually capable of doing this knowledge inverse search question, but this is by a way that is perhaps a little bit cheating. But it gives us some actually like good advice. That is, if in the end of the day there's some piece of knowledge you really want to do knowledge inverse search, then you probably want to augment the data, augment the pretrained data by adding something like line numbers and put the number at the beginning of the sentence and at the end of the sentence and so on. So this can be useful, for instance, for some instructional data. For instance, if there's like 100-line instruction about how to do a task, then you probably want to number them properly, not only with the numbers showing up at the beginning, also at the end of each sentence. In this way, the model, if it's pre-trained on such data, then will be capable of actually doing some inverse search task of asking, for instance, what is the line before a line and so on. So this is actually a pretty surprising result that we found out just with the help from GPT-4. So to conclude, in today's talk, I showed you how to use and how to design synthetic biography data and how to design controlled experiments to test the language model's ability to store, extract, and manipulate knowledge. So I have been emphasizing on this difference between physics and ethology. That is, we are really doing controlled experiments to make very careful and scientific conclusions. Where in contrast, if you only play with GPT-4, then some of you may be able to derive similar conclusions as this talk, but the conclusions may not be like completely rigorous or scientific and so on. So I have been emphasizing on this difference between the two. And there are three main takeaway messages from this talk. Number one is that data augmentation is really necessary on the pretrain level, even for the simplest possible knowledge extraction task, like what is the birthday of a person. So you had better really augment the data. And if you don't, then the knowledge might be really stored in a way that's not extractable, no matter how you fine tune. So that's message one. Message two is that with the current architectures of large language models, then chain of thought is really needed, even for the simplest possible knowledge manipulation task, like asking, testing even or odd for like a birth month and so on. The third takeaway message is that with the current architecture of large language models, inverse knowledge search is just impossible. So that means that we cannot use LLMs as a database, unless you do something like RAG, like Google search to add it as a plugin, or like unless you augment the pre-trained data to also include the inverse order of the data, so that inverse search becomes like a forward search and so on. And in the talk, I also showed you like some probing, but the probing in this talk is relatively easy. The Q probing is actually a known technique, especially like some people actually do Q probing on the internet pre-trained models such as Llama to test, for instance, if is the birthday actually stored on the person's name and so on. So Q probing is not really new, but the P probing is perhaps new, the positional-based probing, because we're doing controlled experiments, so we know precisely what the pre-trained data is, so we can directly feed the pre-trained data into the model to see like where exactly the knowledge is stored. Like, is it early in the sentence or later in the sentence? So this is, I think, one of the one of the good reasons for use controlled experiments, so we can do probing like more carefully. But in any case, like the probing in this talk is still still like quite easy. And if you want to see like more advanced probing, like hierarchically defined probing, then you're more than welcome to watch my talk that will show up later this week on part 1 of our work on studying context free grammar. Okay, so thank you so much for your attention, and I hope you have a good rest of the day. Bye-bye.